Okay, so today's lesson is on functions of several variables. But actually, we only focus on functions with two variables. Okay, if we understand function with two variables, we will understand function with more than two variables. But the graph is more complicated if we deal with the study functions with more than two variables. Okay. So what kind of functions has two variables? Well, there are lots of them. Okay, I'll give you an example. Begin with a example. You know, for example, fxy is going to be square root of 1 minus x squared minus y squared. Right. So this is a function in two variables, x and y. Now, what does it mean? What's the definition of function? A function here, if I draw, you know, it's a map from some domain in the xy plane to another coordinate plane we call z. So some domain. So this is a map. Okay, it's f. So if you give me a point in the xy plane and with coordinates x and y, I can get a number in the z-axis. Okay, so z is determined by this formula. Okay, that's called a function. Roughly speaking, is just a mapping. Okay, now what kind of numbers can be mapped to the z-axis? Well, at least you look at formula x squared plus 1 minus x squared minus y squared cannot be negative. That's weird. Okay, so x squared plus y squared, 1 minus x squared minus y squared cannot be negative. And we will get this inequality. Okay, x squared plus y squared less than or equal to 1 is a disk with radius 1. So any point in this disk can be sent to some number here. Okay, actually the value here is, if this is 0, it's always positive. It's between 0 and the 1, right? The largest possible value is 1. The smallest possible value is 0. So this disk, I'm going to call it D. That's how to describe the disk. Is x squared plus y squared less than or equal to 1. Okay, we cannot use the interval to describe this disk. And this is called the domain of f. Right? It's a domain of f. And the interval r, it's from 0 to 1, is called the range of f. Okay, so this is a function in two variables. A function is just a mapping, right? And we have the name for that. It's called f. You can use different names. And the domain in this case is the disk with radius 1. Okay, and we don't call it circle. Okay, in mathematics, there is a difference between circle and a disk, sphere and a ball. Okay, circle is just one-dimensional curve. It's called circle. And the disk is the region enclosed by the circle. So in elementary school, in middle school, when I look at the textbook, they find the area of the circle. That's not precise. Okay, a circle has no area. Okay, you should say find the area of the disk of the radius 2. So, right? But that usually, you know, say just circle. Find the volume of sphere. Yeah, in mathematics, sphere is a surface, not as a region enclosed by the sphere. Yeah, that was some small difference. All right. So this is a range. Okay. Now, how to define the graph? Okay. we can study the function in another way, put it in the graph. When you draw the graph, the graph of f. The graph of f is an object in three-dimensional space. Is a surface in three-dimensional space. We call it R3. How do you describe it? So we draw in this way. So x, y, z axis, and I move z axis perpendicular to the xy plane. Right now, at the very beginning, right? At the very beginning, this is separate. A function is just mapping. It sends points in the xy plane to a one-dimensional coordinate line. Now I move the coordinate line to the top of the xy plane, and then I make a three-dimensional space. Okay. Then I can describe the function using the point. So here, here's the disk is here. The disk looks like ellipse right now. It's in the xy plane. Okay. So for an arbitrary point, x and y, I can get the z value somewhere here. Okay. So z, so this three components here, x, y, z, and z is going to be given by this function. Okay. So when x runs over the disk, and you get a bunch of points in the space, and for this particular problem, okay, for this particular problem, all those points, okay, form an upper hemisphere. Okay, this is upper hemisphere. Yeah, this is upper hemisphere. Okay, so the graph of f is the upper hemisphere. Okay, for this particular function. And the nearby the circle, the z value is very small, right? When on the circle in the xy plane, when x, y are point according to the point on the circle, then x squared plus y squared is 1. So the z value is 0. So this graph touches the circle. Okay, so you only get an upper semicircle, upper hemisphere. Yeah. So this is a graph of this particular function. Yeah, you can use a function to describe the upper hemisphere. Okay. This is a good problem. Now there the second example. F of x y is going to be 2x minus y plus 1. Now this is a linear function. It is a linear function. Okay. What is domain for this linear function? It's defined everywhere. Okay. Yeah, the domain of f, I use this. The domain is just whole, can be anywhere. Okay. So no restriction on x, no restriction on y. Okay. So x can be from negative infinity, y is also from negative infinity to positive. So this is denoted by R2. R2 means the whole xy plane. Okay. The range, I think the range here will be the whole line. Okay, because for any value of z, you can find xy. So this will be the whole line. It is also denoted by R. Okay, R means the whole line. Okay, R2 means the XY plane. R3 means XYZ space. Now, how about the graph? So the graph of F is the set defined by the equation. Defined by the equation z equals f of xy, right? But if you write down the details, it looks like that. Okay, but I can change the equation a little bit. I use this. This is going to be 2x minus y minus z and plus 1 equals 0. Yeah, this is the equation. Yeah, for a plane. Okay, so the graph is going to be a plane. Okay, it is a plane in the space. For the plane, I want to find a couple of informations, like which point it passes through. Okay, what is the normal vector? Okay, it is a plane in three-dimensional space. All right, so first of all, let's see. I'm going to let x to be 0, y to be 0, and then z is going to be 1. So the plane passing through 0, 0, 1. Okay. This point 0, 0, 1. Okay. And if you let so actually you can write it in the following way: x minus 0 minus y minus 0 minus z minus 1 equals 0. Okay. Or you can write it in the following way: 2 negative 1 negative 1 dot product x minus 0 y minus 0 z minus 1 equals 0. Okay. So this is the normal vector n. Okay. Normal vector. So the picture looks like that. It's harder to draw, but I can just roughly speak. Okay, it passes through the point 0, 0, negative 1. Okay, for an arbitrary point x and y, z, and this is going to be the vector. Okay, so this vector is here, right? And it's perpendicular to the normal vector. It's n. N is going to be 2, negative 1, negative 1. Okay. So equation, the vector equation, the equation for the plane can be described by this inner product. Okay. This dot product equals 0. Arbitrary point, and then you get a vector from one point in the plane to another point in the plane. Then this vector should be perpendicular to the so-called normal vector. Okay, then you get an equation. Okay, so this is about plane. So the graph of this function is a plane. Now in the xy, this is a coordinate system, right? This is a coordinate system. Oh, this is a plus. It's positive one. Okay, not just negative. So the graph defined over the whole xy plane is just a plane above that. Okay, and the z value is determined by z value. This is the x y, and then here's x y z, and the z value is determined by the linear equation. Right. So you got the whole whole plane. This is the simplest graph. Linear function simplest function. Okay. Let's look at another one. Let's look at a quadratic function. Fx y equals equals x squared over 2 squared plus y squared over 1 squared. How about like that? Okay. So in other words, it's going to be quarter of x squared plus y squared. Clearly, it's defined without any restriction on x and y. Then the domain of this f is going to be set of x, y, as long as the function is defined. So clearly, the domain is going to be the whole R2. Okay, it's defined on the whole plane, no restriction on x, unless you want to put a restriction on x or y when you define the function. Okay, now what is the range of the function? Yeah, it's going to be all the positive number, could be 0. Okay, this is going to be half of the plane, half of the line. Okay. All right, now let's understand the graph. Okay. The graph how can I draw the graph? Well, it is always positive, so the the best way to draw the graph is as follows. I consider the equation fxy equals let's say equals r. I'm going to put r squared here. Okay, positive. Right. So I consider this equation. Okay, I want to see what xy gives you the value of what kind of xy gives you the value of r squared. So I get x squared over 2 squared plus y squared over r squared. So I'm going to rewrite this as 2r squared plus y squared r squared equals 1. So this is an ellipse in the xy plane, right? So y equals, this is in the xy plane, and the ellipse. When y equals, x equals 0, then y equals r. Yeah, it's negative r and positive r. When y equals 0, x equals 2r. So this is the ellipse. Okay, in the xy plane. So that means in the three-dimensional space, if this is r squared, okay, and I draw the plane perpendicular to xy plane, then there was here's a circle, right? Yeah, this is the ellipse. Okay, and along this circle, okay, the y value is the same. Or the z value is the same. Right. So above that ellipse in the xy plane, the z value is always equal to r squared. So that you get a curve in this plane, which is perpendicular parallel to the xy. Right. So yeah, so that means for the points on the ellipse in this xy plane, and the z value is going to be r squared. And that means if you want to draw the points I plot the points, you will get an ellipse in that plane. Okay, so Z, okay, every point here, let's put the X, Y, and this is a Z value, right? So X, Y, Z, but the Z is always equal to R squared here, right? Now imagine if you change the value of R, right? And the ellipse changes, the size changes. When R approaches 0, the ellipse shrinks a point, okay? So, so you will get a graph like that, okay? So this is kind of graph. It's a surface. It's a surface. So the graph of function here in 2 variables will be a surface in 3-dimensional space, right? But sometimes we cannot draw this 3D picture, okay? So how can I understand the graph in a different way? I can understand the graph. We are trying to understand the graph in the XY plane only. Okay, let's try to understand. Yeah. In the XY plane. How can I do that? Well, all I have to do is I just draw x squared plus 2. I just needed to draw the graph for different variable R. So as I just show you that this is the x-axis, this is y-axis. Okay. I draw the circle, a famous ellipse. Okay. And then a smaller one, and the larger one. Okay. So for different value, and this one, R could be when I increases the ellipse getting larger and larger. So I equals 4. Here I equals 3. Maybe here's I equals 2. Okay. Fourth, I should, yeah. I'm going to put a K here. Okay. Yeah, use a K instead of R. So K could be 4 square, 3 square, and 2 square. So you get a bunch of the curves, ellipses. Then, if you really want to, so you will get a graph like that. It's a bunch of curves in the XY plane. But you still can probably use your imagination to understand the graph, because you can see that along that ellipse, I know the surface is about 3 square high, right? And around the most inside ellipse, the height of the graph is going to be 2 square. Okay, so this also, yeah, give you all the information you need, but just not the 3D picture. Okay, this is called yeah, those curves are called level curves. Okay, because the graph will be at the same level. Okay, above this curve. Okay, so the curve, yeah, the curves x squared over 2 squared plus y squared equals r squares are called the level curves. Of f, okay, and that tells you how hard the graph it is in the space above this curve, right? Above this curve, and yeah, those are just the definition, the terminology, the level curves, and this is called the contour map. contour map. If you can draw a family of curves, right, and like that, family of level curves, then it's called contour. Yeah. T-O-U-R. Okay, contour map. All right, so if you get the map like that, you can really tell how high the point. You know, suppose you get a map of Indiana, right? We don't have a 3D map inside. You know, of course, like you have Google Map, right? 3D Google Map, you can see, you know, buildings and mountains, especially the mountains, right? It can tell how high the mountain. But another type of map is like this. You get a bunch of curves around each mountain, so you can tell how high of the mountain at any given point. But you don't see the 3D picture of the mountain. But you can use your imagination. Oh, this mountain is, you know, 1,000 meters high, 1,000 feet high. You know, you can tell that. So they just draw several curves, okay? And yeah, there are many applications like that. So you probably don't pay attention. You know, sometimes you can, from the city government, you can even get a map called underground water map, right? And there are also a bunch of curves, and at any point, they tell you what level underground, you know, at a particular point. Yeah, they have this kind of maps. Yeah. So when you buy the house, maybe you should get such kind of map. So it's you know, how much, yeah, water is under that. Yeah. Some areas too much water during the raining days. Yeah. All right. So this is a nice example, and I'm going to do more exercise to understand the functions. So to understand the function, you can use the use this. Yeah, you can draw the graph. You can also draw the graph in a two-dimensional plane in the domain. Its domain. So actually, this is a graph, a bunch of level curves in the domain of the function. Okay, you can also understand the function. Okay, so that's let's look at some problems from the book. I have to give you the homework assignment, right? Some are a little bit difficult to sketch the graph. Some are easier, so it depends the problem. Let's take a look at the next one. Okay. Okay. So I'm going to take a look at number 13. I'm not sure this is a problem, a homework problem now. X minus square x minus 2 and square root to y minus 1. Right? The question is find the domain of the function and then sketch the graph if possible. Sketch the graph. Now find the domain. And you don't have a, you can use a graphing calculator to check your work, but it's not allowed for this, you know, for quizzes and tests. Okay. So first of all, you have to find the domain, right? The domain of f is going to be a set of x and y. First of all, x minus 2 cannot be 0, cannot be negative, right? And the y minus 1 cannot be negative. So you solve these two inequalities, you will get x greater than 2, y greater than 1. So what kind of a domain is, right? Well, you can draw. You have to draw the graph. Yeah. So this is the x-axis. It's y-axis. So x cannot be less than 2. So here's 2. You draw the line. Okay. should be on the right-hand side of this line. Y cannot be smaller than 1. This is a 1. So every point here, the function is defined in this domain. Okay? The function is defined in this domain. Right? So every point in this domain, in this region, y is greater than or equal to 1, x is greater than or equal to 2. So including the boundary of this domain. The boundary of this domain consists of 2 lines, right? It's perpendicular. Okay. Now the difficult part is going to be the graph. The graph. Okay. Almost impossible to draw it, right? So let's look at the value along each side of this domain, right? This domain along this side, I'm going to see along this side the y value is x is not fixed. So y value is going to be 1, right? So when x equals y value is 1, x is then this is just the square of x minus 2. So it's increasing. The value increases along this line. Okay, from 0 to infinity. Okay, and on this side, the value of f x is 2, y value is y, and then this is going to square root of y minus 1 minus y minus 1. Yeah, it's also so both it's increasing along the vertical line when y value increases. Okay, so it's harder to draw it. I'm going to draw it in a 3-dimensional space. Okay. This is x and this y. This is z. Okay. So we the graph is defined here, over here, right? Right. And this is a 2. That's a 1. So let's just like build a roof, you know, okay, over this region. So you have to draw, give me some idea about how does the roof look like, okay, right? And at that point, at this corner, I think f has a 0. But when y increases along this line, fix the x, and this is going to be increasing. It's going to be like that. I believe it's yeah. So it's going to be like this. Okay, above the line above the line above the this horizontal. Yeah, x equals 2, right? And the same here. It's the same here. It's like that. Okay, along this line. Okay, so I only draw these 2 sides of the roof, and you imagine, yeah, it still looks like 3D picture, right? Yeah, and then the middle somewhere. I know it's harder to draw. Okay, anyway, this is roof. I have to this is a roof. Okay, this is a graph. Okay, so that's a graph. It's hard to draw, but you try to give me some information. You know, you build the 2 walls of this building, right? And then in the middle, it's always part. There's loose spin by this, supported by this 2 sides of the wall. Okay. No wonder, you know, students in elementary schools, they have to learn drawing. There should be a class called drawing, you know. Okay, I did not attend any drawing classes, but it's important. It seems to be, yeah. So you will learn some basic skill how to draw a building at least. Okay, that helps you. Right. Yeah, drawing class is important. Even someday you become, something. You probably not going to medical school. Some doctors go to medical. Some students go to medical school. If they know how to drawing, it's really helpful. When you're talking to the patient, where's my pain, and drawing this, the picture quickly. So anyway, I think I already draw the graph. Okay, this looks like that. Okay, and it's getting high and high. If you go away from that intersection point, okay, this is kind of loose, above the two walls perpendicular to each other. Okay. What is the range? I think the z value could be as much as large, and the smallest value is 0. So the domain, the range of this function is going to be from 0 to is going to be 0 to infinity. Okay. Right, so let's look at another problem. Problem number 27. Sketch the graph y equals sine. That. Okay, how do you sketch the graph like this? No restriction on the y value. Okay, no restriction on the y value. So you will so first of all, look at the graph. Okay, we we trying to draw the graph, right? This is the graph. So it's just sine x, no restriction on y. So let's assume y equals 0. So how does the graph look like? It's going to be in the xz plane, okay? So it's going to be like a sine curve, right? So let me draw, this is a vertical. Yeah, right? Yeah, you assume that the y equals 0, then z equals sine x is a sine curve. Since there's no restriction on y, so that means you can extend it. Now it's harder to draw, right? So actually, for another z, for another y value, you will get you will get something like that. Oops, this is parallel. Okay, so to draw a 3D, I'm not good. Okay, drawing. Yeah, I'm trying to draw a 3D graph. But anyway, it's passing through the okay. All right, so now you're going to build a loop on this. Okay, use a different colors. It's good. I think I already finished the graph. All right, so no restriction on y. For any given y value, you can get z equals sine x. It's a sine curve. Then you parallel translate it. Okay, so you get a piece like that. Okay. So this is the graph. And here, this is a y value equals, for example, equals 2, and here's a y value is, it's going to be 1. Here's a y equals 2. Okay. On the plane y equals 2, you get a graph of sine x. Okay. In the XZ plane. Okay. Yeah, you have to catch the key informations. Then you draw that part. Then the graph, it looks like a graph. Okay. Then it looks like a graph. Right. Let's come to a map for the function. I'm not going to draw a 3D graph, just a 2D graph. Okay, and you have to show in the several level curves. So here's the example. F of x. This is problem number 46. Is going to be x times y. All right. So this time I'm now going to draw the 3D graph of the function. Okay, but I do want to understand the graph in the xy plane determined by this equation. Okay, along which curve the function takes the same value of k. That's it. That's it, right? So this is the level curve. What is the meaning of the level curve? Along the level curve, the function takes the same value of k. Okay. Yeah. Along the level curve, okay, determined by k, okay, the function takes the same value. Okay, that's the key point, right? Right. So x times y equals, let's say, equals 0. X times y equals 1. Let's draw this graph. Okay, and x times 0, x times y equals 0. I think either x is 0 or y 0. So you get, this implies either x 0 or y equals 0. So you get two curves, two straight lines. Okay, so you get two straight lines. Now it's hard to draw. It's just x, y axis. When x equals y equals 1, so y equals 1 of x. Okay, so this will be the curve like that. Okay, so k equals 1. K equals 1. Okay, and the axis is k equals 0, y equals 0. K equals 0, k equals 0. The x-axis, y-axis. Right. So now let's look at the xy equals 2. So y equals 2 of x. So in my opinion, y equals 2x is, when x is positive, it's larger than 1 of x. So this should be high there. Okay. So when the x, and this is a point, 1 and 1, right? So it's passing through here. So when k equals 2, right? So you have a bunch of curves like that, I think, they're all still approaches as approaches to x-axis, but in the middle, it's getting away from the origin. Okay, so when k equals 1, it passing through -1, -1. When k equals 2, it is passes through negative square root 2, negative square root 2. Okay, because the product will be 2. And here, when k equals equals 3, and this will be negative square 3, negative square 3. So it's getting away from. Yeah. Okay. So this we have family of curves. This is called the contour map. Okay. It's a bunch of level curves. So in order, this is good enough for you to imagine the graph. What does the graph look like? Because along each curve, it tells you how high the graph it is. Okay. It tells you how high the graph it is. Okay. Along the curve k equals 3, the value of the function is 3. So the graph is about 3 feet above the ground, something like that, right? So you can tell that. Even you do not draw it, but you get enough information. Okay? Yes.
I'm curious if you're asked about the levels that specify 2, 3.
Yeah, usually 3 makes sense. 2 is, yeah, 3 is bad. Yeah, 3 curves enough. Yeah. At least give me enough information. I can see how that look like. Okay. But most of the time, those level curves that look similar. All just needed to do is put the correct position in a where location, right? They're just a family of curves. Family of curves, they have the same type of equation most of the time. All the difference is just the curve that give more than the other one, and that look similar, like this one. They look similar in the same place. Right, so next problem. Right, so problem number, let's see, the even number problems here. Let's say problem number 52. F of x, y equals y over x squared plus y squared. Okay. Now, first of all, look at this function. This can be negative, can be positive. At least you should draw the 3 curves when k equals -1, 0, positive, something, right? So consider this was k, okay? Consider this equation. So k could be, because the function can be negative, can be positive, because the numerator is y value, okay? So let's assume k equals -1. What you get is it's going to be -1, right? So you multiply this out, you will get I think you'll get -y, and if you, yeah, probably change it to k equals -2 is better. It's easier to describe the numbers. You will see that. Let me change this. -2, 0, and positive. You will see why I want to change it. Okay. So complete the square. Y squared plus 2y. Then I add 1 to both sides. So I get x squared plus y plus 1 squared equals 1 squared. So this is a circle, right? Was at the center -1, right? Oh, no, it's -1 here. Yeah. So this circle was radius 1, center to 0, -1. So this is a circle. Okay. And even more general, I guess, for an arbitrary, when you look at k equals 0, the y is going to be 0. So you get the x-axis, okay? So this is when k equals -2. Okay. Now, if you increase and k equals -4, you will get y over x squared plus y squared equals -4, and then you will get x squared plus y squared equals equals -1/4, right? Yeah, let's do this one. So x squared plus y squared plus 1/4 of y equals 0, and you will see that when the k increases, and you get a smaller circle instead of larger. So it's y minus 1/8 of y. All right, and square, so it's going to be 1/8. If you complete the square, just add 1/8 square. Okay, so as you can see that this is a very small circle, but attached to the origin again. Okay, it is very small circle. But when the k increases, a negative number. Okay, then you get this. Okay, so that is when k equals -4. But when k decreases, you get a larger circle. Okay, and eventually when k approaches 0, you will get as a x-axis. Okay, yes.
Yeah, in the last problem.
Yeah, k equals -4. Yeah.
When you did the step of getting the x squared plus y squared equals -2y, we did the simple and then multiply the y to the other side, right? Wouldn't it be a negative on the other side?
No, you're right. You're right. Yeah. That's true. So how can I change it? I don't want to change it too much. Yeah. I'm going to change a little bit. I just put this. Okay. That's good. That's only small change. Okay. So it's going to be like that. Okay. So -4, -1/2. That's right. Oh, that's easy to make mistake. So anyway, so you get a bunch of circles now. As if k is getting, okay, here k is still negative, but k approaches 0, and the circle is getting larger, okay, and then the limit of those circles will be the x-axis. Okay. Okay, so when k equals 0, think about that. When k equals 0, that's the limit case. When k equals 0, y over x squared plus y squared equals 0. That implies y equals 0. That implies the x-axis. Okay. Then when k is positive, this will be the circle above the axis. Okay. So when k equals 1/2, positive 1/2. Okay, then you get y equals x squared plus y squared equals 1/2, and that implies x squared plus y squared equals 2y, and that implies x squared plus y squared minus 2y. Then I have to add the 1 and add 1 to both sides. And the only difference is, okay, this will be the circle above x-axis was radius 1. Okay, so let's go back to the picture and the things we are using. Yeah, I'm going to just use a different colors. So I get, so this is a k equals 1/2. Okay, and you also have a bunch of curves. And when k is getting large, and you get small circles, that shrink at the point. When k getting smaller and smaller, and this is a k goes to 0 from positive side. Okay, this k goes to from negative side, and then you will get they approaches to the x-axis. Okay, so that's it. You just draw a few curves. You can understand how that looks. I think it's harder to draw the graph. Yeah, it's harder to draw the graph. Imagine along the x-axis, above the x-axis, the z value is 0, so it touches. Then it's curved. Yeah, when k, it's not easy to draw. You can use a software or graphing calculator into the function. You can visualize. But at least when you draw the graph, at least this is along the x-axis when y0, and the graph touches down to the passing through the x-axis. Okay. Right. So I'm going to spend a little bit more time on functions of 3 variables. There are functions 3 variables, not just only one. Functions in 3 variables. Functions 3 variables. The simplest function will be x, y, z equals x squared plus y squared plus z squared. Okay, here's the example. How does the graph look like? We cannot draw the graph because we live in 3-dimensional space, and the graph will be 4-dimensional, an object in 4-dimensional space. Okay, you can only see object in the same dimension or lower dimension. That's why you take a picture and hang on the wall. That's a 2-dimensional image of you. Okay, and that you can see it, but you cannot see a picture in high-dimensional space. Now it's possible our universe is embedded in a 4-dimensional space, just like a surface. Okay, so sometimes something all of a sudden shows up and disappear. It will be out of your imagination. But that's possible from mathematical point of view. If our 3-dimensional universe is embedded in a 4-dimensional space, and then some things shows up in, right, and disappear immediately. Just, yeah. So so it's from nowhere sometimes. Yeah. This can be happen. Okay. Now this is so it's harder to draw the graph. The only thing we can do is you draw the contour map. Okay. The level surface this time. We consider the level surface. Okay. Level surface. fxyz equals k. Okay. How does, yeah, so that means in this high-dimensional, 4-dimensional space, the graph Yeah, the graph will be, you have to introduce another variable, could be W equals f of x, y, z. Okay. Yeah, let me consider this level surface. By definition, it's going to be the surface is to be determined by this equation. So it's going to be x squared plus y squared equals z squared equals k. Okay. First of all, k cannot be negative. Okay. So no solution for k negative. Okay. Okay. So if k is positive, then x squared plus y squared plus z squared equals square root k squared. So it is a sphere was radius square root k. So the level surface in the space okay, you get a bunch of spheres. Okay, so here k equals 4. When this is going, yeah, k equals 4, and then the radius is going to be 2. Okay, and here's the radius 1 when k equals is 1. The function, okay, the function. Oops, where's 160? Okay, the function is actually defined on the 3-dimensional space into 1-dimensional. Z equals W equals f x y z. Okay, this is a map. So given given a point in 3-dimensional space, I can get a value called a W. Okay. Now, if you want to draw the graph, it's harder to imagine. Okay. So suppose this will be 3-dimensional space, like x, y, z. I cannot draw it. Okay. This will be kind of surface. Okay. So this is R3 here, x, y, z, and this is W. Okay. It's harder to draw it, but it looks like a parabola, okay, paraboloid. So given 3-dimensional space, so the graph will be in a 4-dimensional space. You cannot draw it. You can only imagine it. How do I imagine it? I will see that for any point on the given sphere in 3-dimensional space, the W value is going to be the same. That's it. Okay. Right. So the W value is going to be the same, and in this case of for the sphere with radius 2, any point on the sphere radius 2, the value of the function is going to be always going to be 4. Okay. Right. So imagine you can view the 3-dimensional space as 2-dimensional plane, then here the circle is going to be just sphere. Okay. Then when the circle is getting large, and the W value is getting bigger and bigger, so you will get a paraboloid in the 4-dimensional space. So it's hard to imagine that actually, because you cannot see it. Okay, this is a sphere. This is a sphere. X squared plus y squared plus z squared equals, for example, equals 4. So k equals 2. Along this sphere, I only draw the 2-dimensional curve. The curve represents a sphere. Then the height of the graph in the 4-dimensional space is going to be 2. Okay, along this over this sphere. So there's a limitation here. That's the reason we can only draw the contour map for the function in 3 variables, because we still can imagine this contour map in 3-dimensional space. It can still see it, visualize it. Okay? And the level is not going to be called a level surface. It's going to be called level. It's not going to call the level curves. It's called level surfaces. Okay. All right. Yeah, it's more complicated. All you have to, yeah, but when you draw the level surface, it becomes a, it's in 3-dimensional space, so you just need to deal with the 3 variables. Okay. Okay. Now, all right. So let's take a look at the graph x, y, z equals y squared plus z squared. Okay. And the question is describe the level curves, level surface here. First of all, the function as always has a positive value. So f x y z is going to be k. Let's only consider positive numbers, right? So in other words, you are looking at this kind of equation. This is in 3-dimensional space. Okay, the level surface is 3-dimensional space. The graph will be in the 4-dimensional. We're not going to draw the graph. All right, so how can I do that? No restriction on x. No restriction on x. So y squared plus z squared equals k. If k is positive, so this will be square k squared, right? Right, it's actually is going to be cylinder. It is going to be cylinder with a radius of square root k. When k increases, you just get a larger cylinder. Okay, so the next one will be a much larger. Yeah, well, I have to use different colors then. That's the problem. Okay, so the next one will be much larger. So when k increases, so you get here's when k equals 4. So this will be the radius is going to be I equals 2. Okay, and that radius to be I equals 1, and then here k equals 1. I think that would be enough. You can say this is a family of cylinders. Okay, going like that. It's just called the level surface. So in the space, you have a bunch of cylinders, and on each cylinder, the function takes the same value of k. That's it. Okay. So see you Monday. No, are we going to have a class on Monday?